There we go. Yeah, I'll send it right now, Kyle. So it looks like Jose's class was, well, just a recording today, more double integrals. But it looked like for me that you're going to be starting what we're doing now on Monday. And he asked you to review eigenvalues and eigenvectors, which we did last time and we'll do today too. So we'll be a little bit ahead. But Rademacher's homework is already up, and there's a lot of stuff to go over for that. He was a few days ahead of us, and I think we'll. When was Rademacher's homework due? Someone remind me. I saw it the other day, but I couldn't remember the. May 7th. Okay, so that's okay. So we've got a little time. Next Thursday. Okay, yeah, we'll definitely get there. If you're working on that, I will get to some of that stuff, especially the last question, the compartment model. I think we need to do a little bit more. What chapters from the book is this? This is 10.2. This is from section 10.2. 10.1 is this is I'm adjusting to the new book as well. 10.1 is kind of a strange thing. They basically tell you a little bit about what we're doing here in 10.2, but then they get into there's not much going on in 10.1. I think 10.2 is really where the meat of what we're supposed to be doing is at here, which is solving these systems. Okay, so last time we did spent most of the time on one problem. I could find it, but we talked about one that was a predator-prey situation. We did all the math, found out it was we called it a source at the very end. We looked at the direction field, and so there's different possibilities of what can happen based on your differential equation. So let's do one more. We're going to do it all the way through where we find the solution to this linear system. And there we go. So we've got this system of differential equations, and I guess I still want to try to attach some context to this so that when we do apply it, which is the next section after this, it'll be hopefully an easier transition. Not all of the differential equations, the systems will lend themselves well to like a, two species like we did the predator-prey model. But some of them do. And so I saw this one in the book, and I was trying to think of a situation that this might model. And this one could model not a predator-prey situation, but some of you probably know this idea of commensalism, where the idea is two species where one is benefiting the other, but there's no harm done from this species that's benefiting. So an example of that could be like you're probably familiar with like suckerfish they live on whales and sharks, and they just attach themselves and they benefit from being on the whale. They get food, they get transportation, I guess. But there's no harm to the whale. Same thing with barnacles. Barnacles will attach themselves to whales as well and get food and everything. There's no harm to it. So if you think about it, like if X was the population of, let's say, whales, this would say dx dt, the rate of growth of whales is proportional to its own size. We talked about last time, this would model exponential growth. Right, if A is 1, if my coefficient of X is 1, and if Y was the population of suckerfish, let's say, let's get Emma in here, then notice that Y's growth rate is tremendously benefited by X, right? There's a huge benefit, right? That's a positive. That's a positive thing, right? That comes from X, from being on the whale. Whereas without the whale, right? If they didn't live on the whale, that you should recognize dy dt equals negative y is exponential decay. They're not going to make it. So they're kind of dependent on the whales and they're benefiting, but you can tell the whale population is not a function of the suckerfish population. There has no effect on it, right? It doesn't matter. So anyhow, I like to, this way I can think about it. Instead of just X's and Y's, I can actually think about a situation here. Okay, so let's get into solving this again. So I kind of broke this down into steps. First step is to put this in matrix form. And recall the way we do that is both of those differential equations. I'm going to write it like this. If we put this in like a matrix or a vector, collectively, these two we're going to call x bar of t, dx bar dt, sorry, dx, yeah. Okay, so this equals, and then we have our matrix, which is made up of our coefficients of x and y. So we would have 1, 0, 4, negative 1 times x and y. Okay, and then recall this had the form of a times x, and we know the solution. We talked about the solution last time. We'll get to it. And we know we need the eigenvalues and the eigenvectors. Now, one thing for the eigenvalues, remember how we do that? We do the determinant of, this is our matrix A minus lambda times I, which ends up being, you put a minus lambda there, so it's 1 minus lambda, 0, 4, negative 1 minus lambda. And when we do the determinant, you get 1 minus lambda, negative 1 minus lambda, minus, remember you do this times this, the main diagonal product, minus the off diagonal product, which is 4 times 0, but that's just 0, right? And so it's already factored for us, right? If this was not 0, we'd have to FOIL this all out like we did on Wednesday and then, add in this number and refactor it. But basically our eigenvalues are staring right at us. It's 1 and negative 1. And you might remember this from 17b. If you happen to get a matrix now in the future where one or both of your off diagonal entries is 0, so this 0 right here, you can see what's going to happen. I'm going to have this times this, and this is going to always be 0 if this one or this one was 0. And so your eigenvalues are just going to be these two numbers here, right? So if you notice that, that's totally fair game. So in the future, so we'll put, how can we put this, note, if one or both of your off diagonal is 0, then the main diagonal entries are your eigenvalues, are your lambdas. Okay, and I'm just going to point back up to here, right? Because of this 0 right here, because of this one right here, these are going to be your two eigenvalues. And so that could save a little time, right? You could just go if you see this, you could just go say, hey, I know my eigenvalues are 1 and -1. Move on, right? Because as you've seen, these solutions can take some time. Okay, now we'll find our two eigenvectors, one for each of our eigenvalues. So we'll assign 1 to be our lambda 1. And remember our definition, it's the matrix times your eigenvector is your eigenvalue times the eigenvector. We'll call this V1 because this will be the vector that goes with lambda 1. So we have 1, 0, 4, -1 times your vector xy equals, in this case, 1 times xy. So we're going to have, if you multiply out the first row, you just get 1x plus 0y, x plus 0y, so that's not even there. And that's going to equal the top entry, which is x. Okay, and I wanted to show you this. We only had a chance to do 2 eigenvectors last time, and we'll probably only do 2 today, but I want to show you different situations. If you recall from Wednesday, both of the eigenvectors I found, I just needed to multiply the top row and I got a relationship between x and y. But sometimes that doesn't happen right off the bat. Right here, what happened is I get x equals x. That doesn't tell me anything. This is true for all x, right? This doesn't really tell me anything about the relationship between x and y. So if that's the case, then you do have a second equation, right? My second equation is 4x minus y. And because I did the bottom row, that should equal y. Maybe I'll put here, no info about x relationship to y. So use, for lack of a better term, the second row, I guess. Use the second row of your matrix. And now I have some information. This tells me 4x equals 2y, which means x equals 1/2 y. So then I can just choose. So remember how this works. You want to choose. There's multiple answers here, but the relationship is my x value, which is the top number, has to be half of y, my bottom value. So because I have x written in terms of y, what I would do is choose a number for y, and I want to choose a number so that I don't get a fraction, ideally. So rather than choosing 1, and in which case I'd have 1 for y and then x would be 1/2, I'm going to choose y to be 2. So if y is 2, that's the bottom number, then x would be 1. Try your second eigenvector. So my second eigenvalue was -1. See if you can find the eigenvector for that one. While you're working, I'll say this. I know Jose's class was doing double integrals. I talked about that at the beginning. and the homework's totally optional. It's WebWorks problems. There's answers I saw, but no solutions, and some of them are tricky. So I've already had a request if I could show some of those. I'm going to write up some solutions for a few of those, and I'll put it on the Canvas site so people in Jose's class can, yeah. Okay, since you have -1 instead of 1. Yeah, let's see. So I'll just go straight to the matrix, 1, 0, 4, -1 equals -1 now times xy. Oh, yeah. So now when I multiply it out, what I get is 1x plus 0y equals -x. Now that actually does tell me something. What's the only number that could go in for x where x has to be the same as -x? The only number that's going to work for is 0, right? The only number who's equal to its negative is 0. So this does tell me something about x, but it doesn't tell me about the relationship between x and y. And that's going to come up too, so I want to show you how you interpret that. Last time I used the second row, so let's try that. Look what's going to happen here. 4x minus y equals -y. Now if I add the y's over to the other side, what I get is 4x equals 0, which once again tells me x equals 0, right? But I get no information about y. So when this happens, what it means is no info about y, and I'll put question mark, right? What that means is y can equal anything, any number. That's what it means. When you get nothing, when you get either x equals 0 or y equals 0, if you don't get any information about the other variable, it means the other variable can equal any number. So therefore, for my second eigenvector, x definitely has to be 0. And if y can equal any number, remember there's multiple eigenvectors, you can pick any number. Once again, though, don't pick 0, right? Because 0, 0 is not really a interesting vector, right? It's just a point, it doesn't go anywhere. So if you can't choose 0, what would be the logical number to choose for y? Yeah, I would just choose 1. Yeah. So I'll put any number. So how about we just choose y equals 1. But if you chose 2 or 3 or even -1, that would be fine as well. We'll talk a little bit more about why you can have multiple eigenvectors coming up here. Okay, so now we have our 2 eigenvectors and our eigenvalues. We had some initial conditions on the first page, but let's write our general solution. So remember, our general solution, one way to write it is x bar of t. That means both x and y. That's a vector form. And remember, our general solution was c1 e to the lambda 1 t times its eigenvector for lambda 1 plus c2 e to the lambda 2 t times the eigenvector for lambda 2. So for us, and now I'm going to, I want you to get familiar with that notation, but I am going to write them separately. This is saying x, which would be a function of t, and y, which is a function of t. So I'm going to put that like in a matrix, is c1 e to the, I got to get this information. Lambda 1 was 1t, and the vector that went with that one was 1, 2, c2 e to the -1t, and that eigenvector we just found was 0, 1. So there's 2 equations there, right? There's x of t is this times the top values of the eigenvectors, and y of t is this times the bottom values. So plugging in the initial conditions, which would be when t is 0, so I want to do x of 0, y of 0. And that's going to be, if I put in 0 for t, e to the 0 is just going to turn into 1. That's also going to be 0. And in this case, I'm going all the way back to the beginning. The initial conditions were 2 for x of 0 and 10 for y of 0. So this would equal 2, 10. And what we can now do is fish out the equations here, right? It's really going to come from here. So C1 e to the 0 is just C1 times 1. That's C1 plus C2 times 0. So that term gets wiped out, would have to equal the top number. So we already got C1. C1 is going to equal 2. And for the second equation, we'll have C1 times 2. So that's 2C1 plus C2 times 1 would have to equal 10. Maybe I should. This is going to equal 1. And that's equal to 1. So I already know C1 is equal to 2, so I think the strategy I'll take here is just plug that in, right? I'll just plug this in here. And that would be 4 if I making sure I got my numbers right. C1, 2. Okay. So then C2 is going to be 6, huh? Okay. So now we can go to our particular solution, and all we're doing here is rewriting this solution with our constants there. So we have, I'll start with the way they'll usually write it in the book. X bar of t is equal to 2, C1 is 2 e to the 1t and then C2 is 6. And it's fine. I wanted to show you this because it's fine to leave your answer like this. You can leave your solution in vector form. As we've discussed, though, there really are two solutions here, right? There's a solution for x of t. Let's write them separately, which is just 2e to the t times 1. So that's 2e to the t plus 6e to the negative t times 0. So that actually just cancels out. And then my solution for y of t is 2e to the t times 2. So that's actually 4e to the t plus 6e to the negative t times 1, right? So just that. Okay. And so there's all the work to get your solution. And then, you'll probably get some follow-up questions now. Okay, so what's the, remember X was representing the population of, in my scenario, the whale population, and Y was the suckerfish population, right? And what we want to know is what's going to happen long-term to both of these populations, right? So long-term means t approaching infinity. So you want to think about the limit as t goes to infinity for x of t and y of t. Move this over. So this would be the limit as t goes to infinity for, keep putting my solution away. It was 2e to the t. And that's pretty clearly, right? That's 2e to the infinity. That's infinity, right? So now, of course, you know, the whale population isn't going to get infinitely large, but, you know, the signal of this is that the suckerfish population isn't going to damage the whale population. It's going to grow to as big as it will grow to, right? Now, what happens to the suckerfish? That one was 4e to the t plus 6e to the negative t. And if you plug in infinity here, right, you have 4e to the infinity plus 6e to the negative infinity. Remember, we've seen this before. How do you interpret that? This is going to get infinitely big. And if I think of this, whoops, somebody coming in. If I think of this as 6 over e to the infinity, this term is going to go to 0. Good. So I'll get infinity, right? So both populations can thrive, right, under this scenario, under this model, with the particular parameters we have. Okay. Now we're going to take this a little bit further. We want to, last time after I finished the problem, I gave you a computer-generated direction field or phase plane. The other name for a direction field is a phase plane. Okay. And, but there's some ideas that I kind of didn't talk about last time. Okay. First of all, when we have a differential equation, this goes back to 17b, we talked about equilibrium, right? Equilibrium points. Equilibrium, by sort of the name suggests, is when there's no change, right? There's no change. And just like we did in 17b, to find equilibrium, we would set not only the first equation, but both of these equal to 0. And we're trying to find numbers for x and y that make both of these equations equal to 0. Okay, well, I mean, the first one, the x is 0, right? It tells us x is 0. And if we plug in x equals 0 there, what are we going to be left with for y? 0, right? And this will be true all of our linear systems. Well, that's a new book. I got to be a little bit careful. My equilibrium is going to be 0, 0. Oh yeah, I know what I needed. That's why I threw in this little bit at the bottom here. This, so terminology, this is called a homogeneous linear system. The homogeneous refers to the fact that the equilibrium for a homogeneous linear system of differential equations will always be 0, 0. Okay. Equilibrium always 0, 0. And this is what we're going to spend most of our time and energy on, is when the equilibrium is 0, 0. And it kind of makes sense, right? If you start with no whales and no suckerfish, if that's where, then you're never going to get any more, right? The system would stay at equilibrium, you know. But to give you an example, so the old book, that was all we spent time on, was homogeneous linear systems. But I've noticed this book has a few examples of non-homogeneous linear systems of differential equations. And so I give you an example of what that would look like. If I had something like dx dt, I'll just kind of modify this. If it looked like x, let's say, minus 2, and 4x minus y, I don't know, plus 1 or something like that, you can tell when it's non-homogeneous if they have some kind of numbers hanging out on one or both of the differential equations. And how that affects it, you can see why. Because if I set this both of these equal to 0, this gives me x equals 2. And if I plug that in here, do the math here, that's 8. Move that over, that's -8. Subtract the 1, -9. Y would be 9. So I get an equilibrium that's not 0, 0. Okay. All right. So but the equilibrium of ours is 0, 0. And okay, you remember when in 17b, I should almost pull up my old notes. Remember when we talked about that section equilibrium, we talked about the idea of it being stable or unstable? And we had this way looking at the, remember we were drawing arrows on the x-axis that were either going to the right or to the left to determine if the equilibrium was stable or unstable. We kind of explore the same idea here. So we're interested in the stability. Okay. Oh yeah, before we get to that. So we're this big axis here, we're gonna sketch a direction field like I showed you at the end of class on Wednesday with some arrows in there. Now without a computer. So there are ways, if you know some ideas, there are ways to get a pretty good idea of what the direction field would look like, okay? One technique is to sketch the nullclines, also called isoclines. And what the nullclines are this. If I go back to my differential equation, dx dt was just x, right? It was just x. And when I set that equal to 0, of course that gives me x equals 0. But graphically, I can draw x equals 0 graphically is the y-axis, right? So x equals 0, let's see. Why don't I do this one? I'll underline this one in red. Okay, that is the y-axis, so I'm just going to draw. Okay, so this nullcline right here is all of the points where dx dt equals 0. Now there's another nullcline. Maybe I'll do this one in green. dy dt, our other differential equation, was 4x minus y. And when we set that equal to 0, that gives us y equals 4x, which is a line through the origin with a fairly steep slope. We'll just make it look like this. Okay, so this is the nullcline y equals 4x, which again is every point on here dy dt should equal 0. Okay. Now what we can also do, we're going to add to our graph, is our eigenlines, our eigenvectors, which we're going to extend into eigenlines. So recall one of your eigenvectors, let me see here. The eigenvector, one of the eigenvectors was 1, 2, right? 1, 2 was our first eigenvector, and that was associated with the eigenvalue of +1. So 1, 2, if I was going to graph that, this here, I don't think the color matters as much as it will for these. So 1, 2, remember to sketch 1, 2, I got to be a little bit careful because this was the line y equals 4x. I'm thinking about like, what would be a point on the line y equals 4x would be 1, 4, right? If x is 1. So 1, 2 would be like going over 1 up only 2. So let's say that's about right here. Even though it may not look to scale, that's okay. So that vector, the vector 1, 2 would, one way to plot it is from the origin over 1 up 2 would look like this. And what you can do with the eigenvectors is actually extend it, and we call this an eigenline. So if I just extend that vector in both directions, this is the eigenline, or I'm just going to call that the eigenvector that was associated with lambda 1 was positive 1, right? This is the eigenvector associated with that eigenvector, that eigenvalue. Which, by the way, this is what I mean by when I say you can have multiple eigenvectors, like 1, 2. If someone had chosen y equals 4, then this would have been 2. I would have had 2, 4. But notice 2, 4 would lie on this eigenline. So the deal is with the eigenvectors, as long as you pick numbers that satisfy this relationship, then it's going to lie on the eigenvector. It's going to lie on the eigenline, which is all that really matters. Okay. Now, remember how when we looked at the direction field, we have a bunch of arrows. So here's an important thing to notice. This eigenvalue of positive 1, if you go back to our equation, the eigenvalue of positive 1 was associated with this part of the solution for both x and y. What does that cause both x and y to do? The fact that this is 1, doesn't that mean the population grows? Whereas when your eigenvalue is negative, we can see e to the negative t actually ended up going away to 0, right? Well, on the other page when we did the limits, right? If you've got an eigenvalue that's negative, that term as t goes to infinity will disappear. So positive eigenvalues are associated with growth. Negative eigenvalues are associated with decay. So here's what you could then do with your eigenline. Every point on this eigenline, if you thought about what's happening to x and y, they're both going away from, remember our equilibrium's right there. They're going directly away from the origin. So your arrows would go outward here in both directions. I'll put positive lambda, arrows point away from our equilibrium, which is 0, 0. Now our other eigenvector was 0, 1, right? And that was associated with the eigenvalue of negative 1. Now 0, 1 is a vector that actually goes right along my null line, right? That's just a coincidence. They don't have to line up, but it just so happens that my second eigenvector is also my null line. Okay, so this is also my eigenvector that was associated with my eigenvalue of negative 1. And so the same deal here. This is causing, if your eigenvalue is negative, go back to the solution. When your eigenvalue is negative, that causes your solution to go back to 0, right? That causes your solution to be 0, which was our equilibrium. So for negative eigenvalues, you can expect your arrows to point inward towards the origin. Okay, now we've got a lot of information. Remember our initial condition was 210, okay? So let's imagine what would happen to our solution if we started at the point 210. Now, 210 would be above the line y equals 4x. So 210, I know I'm not drawing this to scale, but I just don't have room. Let's just pretend 210 is going to be somewhere really over here, but let me just move it over here. Okay, so let's say this was my initial condition. 210. I can now use this information to predict what's going to happen to my solution. I know both x and y are going to go to infinity, but I can get a little more information about how it goes to infinity. So here's how this works. These arrows, I almost kind of think of it as like a current of water. Like if you've ever been in a river, right? These arrows could denote that the river flow is flowing this way, right? It's flowing towards the origin. And likewise, these arrows here give me like the water's flowing this way. So here's what I could expect to happen. The current is drawing this solution in, so it's getting closer to the origin, but this is also pushing it over to the right. So what would happen is my solution would come down a little bit, right? Now here's another thing we can ascertain from this. Remember this null line is all of the places where dy dt equals 0. What does something look like if there's no change? What does a vector look like if there's no change in the y direction? It means these are all, everywhere on this null line, I will have horizontal my solution will cross this horizontally. Horizontal, how about I put arrows? In other words, every solution that goes through here is going to cross horizontally because dy dt is 0. There's no gain in y, right? Every solution would cross horizontally. You know, and we're mainly interested in this region, so I'm not going to draw it throughout here. Now, because these solutions are pushing it to the right, it makes sense that not only do we know they're going to cross horizontally, they're going to cross horizontally going into the right, going to that direction, because that's where the current's pulling us, right? And so what I would expect this solution to do, it's moving downward because of those arrows and to the right because of those arrows, and it's going to cross right here horizontally, and then it's going to start to approach this almost like an asymptote. My solution will go this direction. That's my solution curve. And what you can generally do with these is pick, and I think some professors will want you to do this, is to be able to like analyze it and say, well, suppose for a different scenario, my initial condition was here. I've got all this space here. Let's say my initial condition was here and I had a point there. What would the solution look like? Well, it's kind of the same deal. These arrows would point it, make it go down, and these arrows would make it go to the left. So you could kind of expect a solution to kind of go like this and go this way. Okay. If I had a solution here, it would go upward and then over, right? So my solution here would go like this, something like that. Okay. Now, as far as the stability of this thing, how we classify this, there's almost, you can tell from various starting points that my solution would go away from my equilibrium, right? And that is characteristic of unstable, right? If your solution goes away from your equilibrium, that would be unstable. And it seems like just about every place I could start at would take me away from the origin. There is one scenario where this could be stable. If my initial condition just happened to be right on this line, then my arrows would take me straight to the origin, and that would actually be stable. Okay. You can think of the eigenlines, these arrows, as the strongest current. So if your solution ended up being right here, right on this line, your solution wouldn't have any, it would go straight out. It's going to get pulled. It's like the strongest current, right? It's going to get pulled out. Same thing here. If your initial condition happened to be right there, you would go back to 0, 0. It would be stable. But I mean, what are the chances of that, right? Every other scenario is going to be unstable. So we call this is definitely unstable, stable, and we call this a saddle. Actually, we borrow that name that we used before. We call this a saddle. if it was on the isocline, yeah, if my initial condition heat was here, then what would happen is it would just start off horizontally and go there. It would just pick up where this left off. But you would know it's going horizontal as opposed to down or up, right? You would know it's starting off horizontal. That's a great question. Okay, another final skill here to be able to do. I think you're going to have to do this. I'm not positive, but this is typical in 17C, is to be able to understand how nullclines work and how the eigenvectors generate arrows and how to sketch a solution curve on the phase plane. But we can also use this to sketch individual solution curves for X and Y. So let's try that. Let's say I want to know how is X changing over time. So this will be my population of X. Remember, my initial population of X was 2, right? When T was 0, I started at 2. I need to zoom this out, I think, to see everything here. So what happens to X if you move along this curve? What's happening to your X value constantly? Your X value is constantly getting bigger, right? So you could expect your solution for X to just constantly get bigger, huh? It's just going to keep getting bigger and bigger and bigger. Now, of course, we can confirm that. Where was it? The one I actually use is actually easy. We can confirm that because what is the equation for X of t? It's just 2e to the t, right? And we know that graph. That's an exponential graph. Y of t is a little more complicated, right? To try to graph that by hand. But you can visualize y of t as well. My initial value for y, as you recall, was 10, right? That was 10. That was my starting point. What happens to your y coordinate if you start here at 210? What happens to your y coordinate initially? See how your y value drops? Your y value is actually getting smaller, but then eventually as you move further, your y value starts to get bigger. So if I was to draw an individual solution curve for y, what I would expect is it's actually first going to drop, right? It's going to drop down to some value, but then eventually it will recover and start to grow infinitely big. So if what was y? Y was the suckerfish population, huh? So initially, the suckerfish population would decline a little bit, but then it would, I guess, start to reap the benefits that the whale provides, right, by allowing it to attach itself. I don't know that the whale has a choice, but okay. So what we want to talk about next, I'm kind of out of time. I'm gonna make this a video, and I will run through. There's 3 scenarios when your eigenvalues are real. One of them is a saddle, which we talked about here, and a saddle will always happen. Why don't I at least just add that here? You'll always get a saddle if you have if your eigenvalues have different signs. If I have 1 positive lambda and 1 negative, I'm always going to get a saddle. That's positive. If you were here on Wednesday, we had one where they were both positive, and that was called a source. And then the third scenario is if both of your eigenvalues are negative. Okay, actually, you could probably guess this, because remember, the negative eigenvalue is associated with stability. This negative eigenvalue causes your solution to come back, right? So if you can imagine, if both of these were negative, my arrows would be pointing inward for both of them. And so what that would effectively do is draw every solution in towards the origin. And so that would definitely be stable. And we call that a sink. I had one more page here that I'm running out of time, so but I'm going to make this into a video, and I'll talk about those 3 conditions. And then on Monday, what we need to explore is it is possible when you do your eigenvalues, most of the time, it didn't happen here, But you could end up with a quadratic equation that has imaginary numbers, imaginary eigenvalues. And in the past, we've been taught to just ignore imaginary numbers, but they actually have some meaning here. And those where we get solutions that look like spirals. They spiral around. So we'll explore that on Monday. All right, everyone. Hopefully this is helpful. I'm going to hit stop on my record.